Hello, my name is Ed, and today I'll be presenting QFAST, a quantum synthesis tool that uses a hierarchical continuous circuit space. This work was done in collaboration with the Lawrence Berkeley National Lab, as well as UC Berkeley. Today I'm going to do three things. I'm going to introduce the general synthesis problem, and then give our solution to it, QFAST, the hierarchical synthesis tool. And I'm going to finish up with a comparison with the state of the art. So quite simply, the synthesis problem is given a unitary, find a circuit that implements it. And this enables a few things. It enables algorithm discovery and gate set and hardware exploration, as well as circuit optimization. There's three things we want out of a synthesis tool. The most important is we want the synthesis tool to generate short circuits. This is incredibly important in the NISQ era for correctness. It'll also be more important. It'll be important in the fault-tolerant era for performance. We want their synthesis tools to also take advantage of hardware topology. If possible, we want a synthesis tool to be able to skip any post-processing steps like mapping or routing. We also want our tools to scale reasonably well and be usable in practice. If we can't use them in practice, then there's no fun to be had. Here's a little slide on how important short circuits are. Coherence times of modern hardware pose hard limits on circuit depth. Also, error accumulates over time, and this reduces the depth limit a little bit more. And it's known that long circuits produce erroneous results, which are bad. Here's kind of like what the landscape of synthesis tools looks like right now. We see a few software tools plotted on this graph, where the x-axis is the maximum number of qubits that the tool can handle. This kind of represents scalability. And on the y-axis, we have depth. And this gives an average outlook of how long the circuits produced are. And there's really two groupings here. We have linear algebra techniques like the cosine-sine decomposition up top. And these tools work really well. They produce circuits really quickly, and they scale very well. They tend to produce circuits that might be a little bit too long to produce to run on hardware, modern hardware. And then there's these other groupings like CAC and QSearch. These tools produce short circuits, but have difficulty scaling. CAC, for example, is fixed to 2 qubits, but produces fixed step circuits. And QSearch produces near optimal circuits for the 3 and 4 qubit range, but has trouble scaling past that. We want to be in this green territory where we can produce very short circuits, but we also scale really well past 6, 7 qubits. And QFAST targets this area. And I'm going to describe how we do that. But before that, I'm going to describe QSearch a little bit more because we build on some of the concepts in QSearch. QSearch phrases the synthesis problem as a search plus an optimization problem. It searches over a discrete circuit space. And for each one of those circuits, it optimizes them and tries to find a parameterization of the gates. So here's a little snippet of what that circuit space might look like. And this grows very, very, very large as you get to deeper and bigger circuits. And for each one of these nodes, that's a partial solution. It's a circuit structure that is fed into an optimizer. To give you an example of how, or an idea of how large this is, there is this table over here where we see for a few 4-qubit circuits, just how many nodes are in this discrete circuit space. QSearch, using a smart search algorithm, searches over only a few of those, but this is still a large number. Each one of these nodes, each one of these numbers here, is an optimization problem that is solved and directly relates to the total runtime of this algorithm. This sleep heuristic is something that's built on top of QSearch that reduces the depth even more, but we'll soon see how QFAST reduces this dramatically. And QFAST does this by taking this discrete circuit space and replacing it with a continuous circuit space. And this allows synthesis to be posed entirely as a single optimization step. So let's talk about how the QFAST algorithm works. There's 3 phases to it. There's the decomposition phase, instantiation, and recombination. Decomposition is responsible for taking these big unitary inputs and breaking them down hierarchically into small unitaries. Like I said, this is done hierarchically. For example, we might start with this n-qubit unitary, break it down into a circuit of n over 2 qubit unitaries, and further this process repeats until we get to some small base unitaries, like 2 qubit unitaries or 3 qubit unitaries. And this depends on what happens in instantiation. Instantiation is the part where we take these small unitaries and run them through these small synthesis tools that work really well on small qubits, small circuits, and produce the circuits. This converts from general gates to native gates. This is really cool for a few reasons. One, it makes QFAST composable. We can plug in different tools at this level and gain the properties of those tools. For example, CAC works really, really quickly, and QSearch produces really short circuits for 3-qubit unitaries. So these are things to think about when we plug in instantiation tools here. And we allow these tools to scale to larger sizes by pairing it with QFAST decomposition. Lastly, recombination is the part where we take these small circuits, put them back together. We optimize where possible. We use commutativity and cancellation rules to shave off a few extra gates here and there. And then we get our final output circuit when it's all put back together, and this is returned to the user. Now, the key component of this entire algorithm is really decomposition. So I'm going to spend the next few minutes talking about how that works in a little bit more detail. Decomposition works in a bottom-up approach. We start with an empty circuit, we place another gate, we place another gate, and we keep doing this until we have a circuit that implements the unitary that we're after. So there's two things to think about when we're placing another gate. We need to think about where that gate's going to go and what is that gate going to do. To give you an example of how this was done in the past, QSearch searches for the gate location, and QSearch optimizes for the gate function. But we have a way of doing these at the same time in one optimization problem. Let me talk about that a little bit. We take the locations and we encode them in a continuous fashion that multiplexes all possible locations and functions. We pass this to the optimizer, and the optimizer solves for both the location of the gate and the function of the gate in one go. It's worth noting that topology can be encoded at this step by restricting which locations the optimizer can pick. And like I said, this allows synthesis to be posed as a single optimization step. So remember that table that we saw previously? This is the QFAST column added on the side. We see a few orders of magnitude improvement here. So this is how it works. We have to start with the building block, this general unitary. We use a poly construction for general unitaries, and this gives a parameterization of any qubit-sized unitary operation. So looking at this simple case, any single qubit operation can be constructed using this exponential of a weighted sum of polys. And what's really cool about this construction is that the coefficients, these alpha coefficients, really determine the properties of this operation. And this concept scales naturally to larger size problems. If we want an n-qubit operation, all we have to do is replace these polymatrices with nth order polymatrices. An nth order polymatrix is just a tensor product of n polymatrices. And likewise, these alpha coefficients determine the properties. And what's really cool about this, if we cleverly select the alpha coefficients, some of them, if we set them to 0, then we can encode location in here. So let me give you an example of how we do that. What we're looking at here is a 2-qubit system, and we're multiplexing 2 single qubit locations and all possible single qubit functions. And this is the encoding that gives exactly that. This is the QFAST encoding. What we did here is you can notice that we took the second order polymatrices and we removed a lot of them and we grouped them. So in this first grouping, we see 4 polymatrices all having an identity in the second position. What this corresponds to is a single qubit operation on the first qubit, qubit 0. And the second grouping likewise corresponds to a single qubit operation on qubit 1. And that's because you see the identity in the first position, meaning don't do anything on the first qubit. And these L variables here determine which grouping is being selected. So if L0 is 1 and L1 is 0, we throw this away. We keep this first grouping and we've selected the first location. Likewise, we can select the second location by setting L0 to 0 and L1 to 1. And these alpha coefficients here determine the function of that gate. So this is an encoding, a continuous encoding that encodes location and function. Pass this to an optimizer, gives you back values for L and alpha, and you get a function and a location of a gate. Okay, so that's the algorithm. There's a few notes I want to make about the algorithm. There's a trade-off in how you choose the block size. So for example, if you're given a 4-qubit unitary, you have to decide, are you going to break that down to a 2-qubit unitary blocks or 3-qubit unitary blocks? If you pick the smaller sized blocks, you'll have a higher probability of getting a shorter circuit as a result, but it'll probably take longer to converge. Like versus if you pick a larger unitary block, say 3 qubits in this example, then you will have a higher chance of converging quicker, but will probably have a longer circuit. So there's a trade-off there. There's also an important note here that the quality of solution of the final solution depends largely on the synthesis tool used in instantiation. So for example, you do this really good job taking this big unitary and breaking it down into small 3-qubit blocks. And you're deciding whether you're going to use a cosine sine decomposition tool to convert these 3-qubit blocks to native gates, or if you're going to use Q-search. If you pick the CSD tool, then you'll very quickly get back 20 C0 circuits. If you pick the Q-search tool, it might take a little bit longer, but you'll probably get back shorter circuits. And when you put them all back together, this makes a large impact on the final quality of solution. And there's a trade-off here. Of which synthesis tool you pick to use during instantiation, you got to think about what the properties of those tools are and which ones you want to really escalate into QFAST. And last thing to note, there's a property that we want to enforce on the optimizer. We want any gate to have a different location than a previous gate. And we do this by partitioning the set of locations into 2 disjoint sets. And we tell the optimizer that even indexed gates can pick from one set, while odd indexed gates can pick from the other set. And this enforces that property that you'll never have 2 gates in a row that are on the same set of qubits. Okay, so let's talk about the evaluation. We implemented this in Python 3.6 using TensorFlow 1.13, and we used the Atom optimizer from TensorFlow. We ran all of our benchmarks on a 2 CPU node using Xeon Haswell. There's 32 cores in total and 128 gigabytes of memory. The benchmarks that we used are several benchmarks that you might find commonly in literature, physics and chemical circuits, as well as several algorithms and gates. We compared our results to Universal Q's cosine sine decomposition compiler. So let me introduce the results here. There's a table here with 3 major columns. In this first column, it's the benchmark column. These are circuits that were generated using domain-specific synthesis tools. You have the name, the size of the system, so this is 5 or 6 qubit circuits, as well as the depth. The depth here is the number of C0s. We don't count single qubit gates. The QFAST plus UQ column uses QFAST decomposition with Universal Q as an instantiation tool. We take these 5 and 6 qubit circuits, break them down to 3 qubit blocks, which then we feed into Universal Q and put back together. The Universal Q, this third column over here, is calling Universal Q directly on the 5 and 6 qubit unitaries. There's a few things I want to point out. First, QFAST reduces the depth by about 6.3 times on average versus the domain-specific synthesis tools. QFAST also reduces the depth versus Universal Q by about up to 10 times. The last thing I want to note is that QFAST is not optimal. If there is a really good domain-specific synthesis tool, like there is in this example of QFT5, QFT6, and Grover, we do worse. To conclude, QFAST scales these synthesis tools to the 6 to 8 qubit range. And there's a really strong argument for using good instantiation tools. QFAST is composable and retargetable. You can plug in these different synthesis tools, CAC, Q-search, and Universal Q, during instantiation and gain the properties that those tools have. And also, since I've collected these results, we've improved the performance of QFAST by a considerable amount, by 10 times. There's active development going on it. And there's actually, here's a link to the code where you can find it right now. There's a QR code there. And thank you. Thanks for listening. I would be happy to answer any questions at this point.
OK, thanks a lot, Ed. We have a couple of questions coming in on the Slack now. The first one is from Peter M, who asks, which part of TensorFlow are you using in QFAST?
So we use the optimizer. It's really just an optimization problem. TensorFlow gives us a very nice framework for just quickly building this out and then running it on an optimizer. but we are working on a version that has removed TensorFlow. We've used other optimization packages, and we're seeing more improvement in performance and quality in that regard. But this is an active development.
Okay. Now, Ross Duncan asks, what are those TFIM benchmark circuits? Namely, what kind of circuits are they?
So these are transfield Ising model circuits that were produced by a colleague of mine, Lindsay Bassman, at Lawrence Berkeley National Lab.
Okay.
These, what we're seeing here, these different numbers are time steps of the model.
Okay. Yeah, so if there's no more questions on the Slack, I'd like to ask one, which is about this disjointness condition between your successive steps. So why do you enforce that?
The optimizer is silly. Sometimes it will pick the same gate, the same location for consecutive gates, and this really doesn't do anything to progress the algorithm. So we observed that early on, and we came up with this method to enforce that rule that it has to pick a different location for a new gate.
So is it true that your parameterization is actually universal for its support? So you can actually get any unitary gate on the qubits that are there? Or
Yeah. So if we go back here, this part right here, so this part right here is really the same single qubit in construction projected to a 2-qubit space. And so that's grouped over here, and then we have the other single qubit grouped over in another case. This extends to all sizes of gates and all sizes of circuits. And this is universal. This encoding right here is any single qubit operation. In fact, if you just take these alpha variables, take them out of this equation and plug them into this equation, you get that single qubit operation. And that's how we pull the gates actually out of this encoding.
Mm-hmm.
And so, yeah, this is universal, that if we are working with n qubit sized gates here, then that would represent any n qubit operation. We work in this generic gate space, and we rely on instantiation tools to convert from our generic gate space to native gate spaces.
I see. Okay. I see that there's one more question being typed. Might take a minute here.
No rush.
That's
So if there are any other questions that come up throughout the day, I'll also be on the Slack channel, and I'm more than happy to answer any questions that come up throughout the day. I do hope that I'll put back this link up here. I do hope that some of you go and check out the code and try it out. That would be awesome. I can be reached by email too to discuss these even further in the future.
great. So as a final question, it's from Will Simmons. During the optimization example you gave, you reused the alpha variables between different groups. Does this connection between the groups impact how the optimization searches the space and converges?
Yes, it does. Not in a very profound way, but you will get slightly different results if you use different alpha variables or not. We chose to use the same alpha variables because this reduces the dimensionality of the problem by a significant margin. When you scale this up, there's a lot of variables that come into play. So we chose to reuse the alpha variables. It doesn't really make that big of a difference, but it does make a slightly noticeable difference.
Okay, thanks. And yeah, I'd suggest you go on to your Slack channel and see if anyone else wants to ask any further questions. So thanks again, Ed.